Hi, it's Len. This will be the second and last, I'm sure you're happy to hear that, of the PowerPoint films that I asked you to look at and think about. It's going to be build on yesterday's in that yesterday I talked about different definitions of the climate and climate change, and I didn't say it outright. I tried to seem open-minded, but I think you probably picked up that I thought that the systems definition was the best of the ones being out there. And you may be aware that systems and system models is considered one of the cross-cutting currents in the NGSS, and it turns out that this becomes a really good opportunity to integrate technology and math. We're not going to talk about much engineering, but a lot of what today's going to talk about is some very, 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 very advanced computer modeling. And we're going to deal with two sets of models. One of them is not very well understood by the public, and the other one is communicated to the public with amazing grace every single day of the year. So you have probably already guessed what I'm talking about. The first of the models are the weather models, which are amazingly complex computer models, and the results of the model end up being communicated to the public in something like this. And I want to focus in on this probability of precipitation thing. There it is. It says 10% probability of precipitation. And in a second, I'm going to ask you to pause and think about a question. So here's the question. What does 10% POP mean? So if a weather model says there's a 10% probability of precipitation in Athens on Saturday, what does that mean? Okay, I hope you wrote it down. If not, I hope you have a clear idea in your head that you can remember when we get back to this. So first of all, how did that number get come up with? And then we'll talk about what it means. They use these computer models called weather models. What they do is they simulate the whole atmosphere of the Earth. They take the surface of the Earth and the oceans as a given. They sort of know where there's warm water in the oceans. They feel like they know how fast the currents are flowing. So they just take that stuff as a given, but they figure they don't really understand the atmosphere. So they divide the atmosphere up into a whole lot of grids. Each of the grids is around 69 miles. That's actually 60 nautical miles is what it really is on each side of the square. And then different heights. The closer you are to the surface of the Earth, the thinner they're slicing the atmosphere. And then, if it's an area where it really needs to be fine-grained, like over very, very unusual terrain, over the Rocky Mountains is going to be more finely grained than over Kansas, for instance, just east of Colorado. Over a city where there are a lot of people who really care about the weather forecast is going to be more finely grained than over, Siberia or someplace like that. And then what they do is they collect all of this data from all of the weather satellites and weather balloons and weather stations in the world. There's so much data about the current state of the atmosphere, you would be shocked. They load that into the model, and then they use basic physics, how fluids move. The field is called fluid dynamics. They use basic equations that are well understood in the world of physics, and they say, what will this system look like half an hour later? And then they say, what will it look like a half hour after that and a half hour after that? And they run it and they run it and they run it until they have some prediction of what it might look like on Saturday, for instance. So that's basically how it works. But there's a complication, and I think a lot of you may be aware of this. It's called the butterfly effect. For those of you who aren't aware, the butterfly effect actually came from the earliest days of computerized weather modeling. There was this guy named Lorenz. He developed the first computerized weather model. And what he was doing, so one day there was this very interesting output from the model, and he wanted to look at it again. So what he did was he printed it out. He printed out the state of his weather model at this particular point, and it was all these numbers on, these piles of paper. And then he had one of his grad students go back into the weather model, and by hand he re-entered the numbers from this earlier run. And then they ran it again. And what happened was really unexpected. They were actually kind of expecting the exact same result, but that's not what happened. What happened was the first day was really close to the other time they ran it. The second day it was a little bit different. The third day even more different. Fourth day, fifth day, sixth day. And by 10 days out, it was like they were dealing with two completely different weather systems. The models couldn't have differed more if they tried. And Lorenz was really puzzled by this because, he had a printout of the data, they entered it by hand, he double checked it, they did it exactly right, no problem, they entered it correctly. In fact, when they re-entered it by hand, they got the exact same results. It was really weird. And then he realized what had happened. In the computer memory, it stored something, I'm making up the numbers, I don't remember exactly. It stored 6 digits for these numbers, so like 6 decimal points. On the printout, he only had 4 decimal points. So the two computer runs were identical for every single characteristic of every point in this weather model. Every weather constituent were identical to 4 decimal points at every single point. But they differed on the 5th and 6th decimal point. And that difference ended up making all the difference in the world as the system played out over several days. So what the butterfly effect means is the idea that if a butterfly flaps his wing in China today, as a direct result of that, in 2 weeks, there might be a hurricane in New Orleans. That's the butterfly effect. So a very, very small change in a complex system as it plays out over time can have huge impact later on, okay, in ways that are very unpredictable. So this would seem to make computer modeling of the weather virtually impossible. But they actually came up with a very clever solution to their problem. Here's what they do. They call them ensemble modelings. So they sort of admit, you know what, all of this data we're getting from all of our satellites, we're only getting 5 decimal places worth of data. They're not giving us 8 decimal places worth of data, but there's no reason for us not to put 8 decimal places worth of data into our computer models. So what they do is they enter the exact data that they get from the satellites into the models, and then the computer generates a few extra random digits for all of these criteria. And they run the model. And then they put in the real data, and then they generate another few different extra random digits, and they run the model, and they get a different result. And then they do it again, different result. And they do this like 100 or 1,000 times. And you actually, without knowing it, you may have known this already because they communicate this very effectively to the public. Here's what you would have seen on TV, what was it, 4 days before Sandy hit New Jersey. What they'd done is they had all of this data about the state of the hurricane, and then they fiddled with the last 5 digits and they ran it. And maybe one time, it went off into the northern Atlantic and they ran it again, and the next time, it hit South Carolina. Then they ran it again and it hit New Jersey, and then they ran it again and it hit Virginia, and then it hit New York, and then it hit New Jersey again, and then it hit New York, and then it hit Pennsylvania, and then it hit Jersey, then it hit Delaware. And after a while, they were able to say, oh, there's a really, really high probability that this thing's going to take a left hook and go into the greater New Jersey area, right? And it's really remarkable because in the whole history of meteorology in the Americas, nothing like this had ever been seen. So they actually predicted a very, very, very weird event that had never happened before in all of observed human history by using this climate model. It was actually quite a remarkable success. And then from a science communication point of view, I think the weathermen on TV actually did a pretty good job with these pictures of the ensembles. I think they did a pretty good job of communicating how the modeling was working. So anyway, there's that. That's weather modeling. So let's go back. What does 10% probability of precipitation mean? One thing that it might mean is that in 10% of their ensembles, there's a trace of rain someplace in the Athens Greater Athens weather area. I don't know what our weather report covers. Or what would make a lot of sense if you're interested in seeing how well your models are working and how well you're predicting, and you really want to make sure that you've got good data on whether or not it rained, it could be that 10% of the ensemble said there would be a trace of rain at the weather station, because then you can check your work, right? Maybe it's a trace of rain, who cares? Maybe it's at least a tenth of an inch of rain at the weather station in 10% of the models. Or maybe it's not about 10% of the models. Maybe it's 10% of the area got rained on in 100% of the models. Or maybe in 50% of the models, there was rain in 20% of the area, or the other way around, right? So if you just think about this, there are actually an infinite number of different things that 10% POP might mean. And I may have mentioned that one of my committee members used to be president of the AMS. He was actually mistaken because a colleague of his, who I took a whole course on POP with, a colleague of his actually called up the guy at the National Weather Service station here in Athens, right? And asked him, and it actually means something very different. I'm overstating this. Here's what it really means. It means that he is communicating with the public, and he understands that the public doesn't really understand computer modeling. So, and you wouldn't know this, but once you hear it, you'll go, oh yeah, of course. I chose Saturday in July for a reason. Well, I chose July because it's July, but I chose Saturday for a reason. Let's say you're getting married on Saturday and you've been waiting for this day your whole life. And let's say not only have you been waiting for this day your whole life, but because your father loves you so much, he has spent, I don't know, $30,000 to make this a beautiful day for you. Then let's say that the weatherman says, oh, there is a 1% chance of rain on Saturday. And let's say you hear that, your brain, you can't deal with 1%. What the hell is that? That's zero to a layperson. So what you do is you decide, you know what? I'm going to save the $50. They probably cost more than that. I'm not going to rent the tent. We don't need the tent. It's going to be a sunny day. And then guess what? It rains. And guess who gets a furious phone call Sunday morning? This guy. So it is only under very, very, very extraordinary circumstances that you will ever read a weather report that says 0 or 100. Okay? If this guy thinks there's a 1% chance of rain, he's going to tell you there's a 10% chance of rain. The other thing is this part of the area, you know, the weather station, all of that stuff, that's purely a judgment call. Every National Weather Service person makes the judgments based on their understanding of the local community. It's not just the area. If the weather model says it's going to rain a lot in Oconee National Forest, but it's going to be bone dry in downtown Athens, he's going to say that there's a very low chance of rain that day. So it's not even as simple. It's like where he thinks it's going to rain. Are there people there? It's purely a judgment call on this guy's call at the end of the day. It's a judgment call that's well informed, but at the end of the day, he makes a judgment call, and his judgment call is based on his understanding of how people will receive the news that he gives them. Because they're cautious, they tend to skew towards 70 or towards 50%, because they don't think the public, you know, understands that if you tell them, oh, there's a 5% chance of rain, and if you say that 20 times, and it rains one of those times, that they nailed it. The public doesn't understand that, so they tend to skew towards 50, but they almost never predict 50. And the reason they almost never predict 50 because if they say 50 to the public, then the public hears this guy doesn't have a clue whether or not it's going to rain. And sometimes 50 would be the exact dead-on right prediction to make, but they're never going to make it. Yeah, I shouldn't say never. You're very rarely going to see that. Okay. So there was some other weird weather in 2012, and let's see if I can. Why does that not work? Let's try that again. Okay, there it is. So we're going to look at some weather that occurred in 2012, and it is not Sandy. If I can get this thing to work. It doesn't work this time. Okay. Sorry, folks.
This summer 2012 was an
Huh. There.
This summer 2012 was an incredible experience and an incredible time to be on top of the Greenland ice sheet. This July, 97% of its surface began to melt for the first time since 1859. It just so happened that we were there
talk about
exactly
1859 later.
when this was taking place. Imagine the world's biggest water slide park with streams running everywhere. Everything is melting. Water is running off into these incredible blue, spectacular rivers, which are beautiful yet deadly.
A lot of the streams are actually maybe 6 meters from the bank, and then if you fell in one of those, then you're done.
We actually set up a camp on top of the ice sheet in the melt zone.
We have a 10 feet by 10 feet tent, and there are only like a couple of mounds that we can even get the thing on.
The reason the Greenland ice sheet is so important to the world as a whole is because it holds an enormous supply of ice. If all of that ice were to melt, it would raise sea level by about 7 meters, which would wipe Florida off the face of the earth.
We don't really have a great handle on how much of that water that's actually melting on the surface is actually making it to the ocean.
Okay. And I said we were going to talk about 1859. It was a very weird year in terms of solar weather. There were some very, very exceedingly active solar flares. There were not people on Greenland at the time monitoring how much of the surface of Greenland was melting, but people who study Greenland and Antarctica have noticed signs of widespread melting that year, and there's also records indicating these very, very active solar flares. So they think that there was exceedingly unusual solar weather that year that impacted the Earth's weather, and specifically the weather of Greenland. But he doesn't know that maybe it was 100%, maybe it was 50%. All they know is that it was an unusually high level of melting happened in 59. They don't know how much. They do think they understand why. So anyway, let's forget about 1859. We'll come back to it in a second. So let's just use the traditional model of climate, the mean and variability model of climate, and let's ask how weird a 97% surface melt is. And so here's a graph, a very recent one, and it's about the amount of the surface of Greenland that is melting at different months during the year. And if you look in July at the peak of the melt, on a typical year there's around 25% melting. That's the blue line. And then standard deviations are a measure of variation, and 2 standard deviations above normal seems to be around 45%. So 2 standard deviations covers what happens basically 95% of the time. So here goes. So we've got this, and then if we're using the standard mean and variation model of climate, what we see is that 95%, which is very, very close to 97%, is 7 standard deviations above the mean. So that's fairly unusual, but let me give you a way to see exactly how unusual it is. I'm not going to go into all the details. It's called a z-test. It's an important statistical test. It's something worth learning if you're not familiar with. It may be even something for your brighter students to teach them, because if they start doing z-test and t-test on their science fair projects, it's little things like that that get judges' notices, and you start winning science fairs if you do these little things. So anyway, put that aside. And you know what I mean, like regional science fairs and stuff. So when you run a z-test, it turns out that under this traditional mean and variability definition of climate, The event that happened in Greenland should happen around 3 every 100 trillion years. Now, I don't know if you think about this very often, but we think the Earth is only 4.6 billion years ago. So basically, you would need to have 50,000 Earths, something like that, for this to happen 3 times. Ever in the history of 50,000 Earths. I think the mean and variability model is broken. It is not working. Heck, it might even happen in 1859. This cannot be a 3 in 100 trillion kind of event. So, what's going on? The reason the classical model doesn't work is because Greenland is a complex system. And there's a very specific aspect of it. So, and you can almost see it here. It's like right in front of your eyes right now. So here's Greenland with some little melt ponds. And what you'll notice is that the ice is white, but the water is dark. And as you know, dark things absorb sunlight, white things reflect sunlight. So when the light hits the ice, it gets reflected back into space. It doesn't significantly heat the ice. It heats it a little bit, but much, much less than when it hits the water. The water is dark, the water absorbs the sunlight, the water gets warmer. So let's say you have an unusually warm spring in Greenland, and you get some unusually large ponds. These unusually large ponds absorb an unusually large amount of incoming sunlight, which makes them larger, which makes them absorb more sunlight, which makes them larger, which makes them absorb more sunlight, and before you know it, 97% of the surface of Greenland can be melting. Okay? What I just described is a very, very famous phenomenon in climate science. It is called the ice albedo feedback. And what was happening in Greenland was not that the conditions of the atmosphere were terribly unusual. In fact, it wasn't even the conditions of the ice sheet were unusual. It was the normal workings of the ice albedo feedback, but it led to an event that was striking for people who were there. So how are we going to deal with trying to understand things like the melting of Greenland? And I think you know that if Greenland were to rapidly melt all of it, that would be nothing short of a disaster for the human population. So they have these other more complex models. In essence, they're like the weather models, but they're different. They're called either general circulation models or sometimes global climate models. There are subtle differences between those two, but they're GCMs. Let's just go with that. So, like the weather models, the GCMs include the atmosphere. But because the ocean can no longer be taken as a given, when we're concerned with climate change, the way the water flows might change. They now do the same sort of thing where they divide the whole ocean up into a grid. They use the formulas of fluid dynamics to understand how the ocean moves, and they include that in their climate models too. In fact, what I just described, that's technically a general circulation model, the atmosphere and the ocean. In the global climate models, what they also do is they try and model the very, very complex behavior of the cryosphere of the ice. And then also here they have vegetation, but that's really the biosphere and land surface combined. So they try and model what's going on with the biosphere, they try and model what's going on with the ice. Easier to model the oceans and the atmosphere because they have some experience, at least with the atmosphere, which is also fluid in terms of the weather models. But it's very similar, but there's some real complexity well, there's complexity in every aspect, but there's a higher level of complexity on the other two. Okay, but despite all this complexity, they turn out to do a pretty good job. Let's just zero in on the bottom one. If you back up, you'll see the whole thing. But what they've done here is they've done a little bit of post-dicting. So once they have their models running, they're able to change things in the models. So they can say, oh, what would happen if we made the atmosphere have this much carbon dioxide, or we made the land cover look like this in 1910, and then we ran it forward, whatever. And so what they're able to do is run models using, basically what really happened, natural and anthropogenic forcings, and then run models as though human beings hadn't been cutting down forests and hadn't been, burning trees and hadn't been burning fossil fuels and stuff like that, and building cities, all of those things. So when they compare the two sets of models and then they look at the data, the two models not only differ very significantly from each other, but you can also see that what actually happens is generally very, very much within the frameworks of the model. Once in a while, you might see an occasional blip in observed data outside the model, but they tend to do a really good job, at least of post-dicting, right? But of course, that's not yet predicting, and so it questions how useful the models are. But it's impressive in its own right, given the complexity of the models. Okay. In order to get a sense of what they might be used for in the future, I want to look back at the most recent winter. I certainly remember what went down here in Athens. It was pretty remarkable. At the same time as we were experiencing extreme cold, Australia was experiencing record-breaking hot. It was I think, even weirder weather from the Australian context, though I'm not an Aussie, so I don't really know what it was like down there. And I'm going to focus in on the very, very high levels of flooding or rainfall in general over the course of the whole winter in Great Britain. And it's not because that was the most weird event during last winter's weather. There was a lot of weird weather. But because there happened to be a lot of climate modelers who live in Britain, and they came up with something really cool and original, and I want to share that with you. So here's basically what they did. They did the same thing that we were talking about here, but they focused in on just like that year. And they ran two ensembles of models. The first ensemble used the current condition of the climate in terms of, atmospheric CO2, land use, all of that stuff. That's what's in blue. And then the green one used some historical model. I don't know exactly what the details were. And then what was really cool about what they did is that they didn't have access to the powerful supercomputers that they would have needed to do this the way you would really want to do it. So they turned it into a citizen science project, and all of these people volunteered spare computer time on their computer, and they got a whole lot of volunteers. They want to be able to do 30,000 runs to have like enough data in their ensemble to give a meaningful answer to what happened in 2014, or this winter. But this will give you a sense. So let's not look at 435, which was the level of rainfall they have. And if you look here on the graph, you'll actually see that in their 2,000 runs, they actually haven't had any event under either the new climate or the old climate that was as high as 435. So let's look at 350. And if you look at 350, you'll see where it intersects the blue line, that's the modern climate line, and then you go down. It's a logarithmic scale, and it's a little bit less than 1 out of every 8 years that you would expect to see 350 milliliters or millimeters of rainfall in Great Britain during the season, and under the current climate conditions. But if you run the models using ancient or historical climate conditions, then what you'll see is that same thing. You follow the line down, you see the second line here, logarithmic scale, sorry it's a little fuzzy, that's a little bit more than 1 out of every 20. So it seems that in this hypothetical 350, and obviously there was much more rain last winter, but to get the idea, in this hypothetical 350, it would be 1 in 8 chance in the modern world, 1 in 20 in some hypothetical, Eden that doesn't exist anymore. And let's think about what you could do once you have this. So let's pretend that we like the numbers 8 and 20, and because we like the numbers 8 and 20, we love 8 times 20, which is 160. And we'll ask how many flood years at this level there would be every 160 years under this scenario. And under the new conditions, 1 out of 8, you would expect to have 20 flood years. Under the old conditions, 1 out of 20, you would expect to have 8 flood years. So if in 160 years you would have 20 floods under the modern climate, and 8 of them would have quote unquote happened anyway, you can sort of, in a weird way, say that 12 of these floods were caused by climate change. Of course, you can't say which ones were caused by climate change, but you can, in a way, say 12 out of 20 floods were caused by climate change, and 12 out of 20 are 60%. So you could get to the point where the weathermen could go on TV and say, there was a 60% chance that this year's flooding was caused by climate change. But because climate models, or not climate models, because computers get faster and faster and faster all the time, something that we need lots of computers to do today and several months to do today are the sort of thing that in 10 years with a supercomputer you might be able to do on the day that the weather event is happening. And I'm half expecting that within 10 years, along with your weather report, the weathermen will be able to say there is an 80% chance that this storm is due to climate change, or there's only a 20% chance that this storm is due to climate change, which means there's an 80% chance that that it's not due to climate change, that it quote unquote would have happened anyway. You might even be able to say, this storm is less likely under the new scenario, under the new climate, than it would have been in the olden days. Like that, it's really odd that this is happening in a climate change scenario. And it becomes possible for the weathermen to communicate about the weather information about the climate. And there's this thing that we always say in talking about weather and climate that, you cannot say that any single weather event is attributable to climate change. And it's true that you cannot say that it is definitely because of climate change. But you can make the kind of probabilistic statements that weathermen make every single day, and in fact have a lot of skill in making, and they have a lot of understanding of how the public receives probabilistic information and how to communicate that kind of information to the public. So this is something that I think could really, really change climate communication over the next several years, and it will probably start to happen during your teaching career, and it'll be good if when you see it happening, you understand what's going on behind the scenes. This would not have helped us with something like Greenland. And the fact of the matter is that the modeling of ice sheet behaviors is really, really difficult. And if there's a recurring theme in the history of global climate models, it's been their inability to model what's happening in the cryosphere. And basically, none of the models ever suggested that anything remotely like the positive feedback loop that I described, and intuitively it's very easy to understand, but the models simply are not able to predict what's going on, and there are good reasons. It turns out there is a lot that we don't understand about ice sheets. To just give you one example, we do not know what is underneath the ice in Greenland. There is a real difference between a depression in which water can pool and a channel that would carry water into the ocean. If we want to understand how fast ice sheets will melt, we need to understand what is underneath the ice. Okay, I'm not going to list all of these, but it just gives you a sense that there is a lot that we don't know. I'll focus in on one of them because I used a word that you might not know. Fern that's the middle one, meltwater retention of fern. Fern is a state of water that I have never seen. I have only read about it. But as snow is getting compressed and it eventually becomes glacial ice, in between it becomes this other material that I've never seen, I've read about, I won't even try and describe it, but they call it fern. It's neither ice, neither glacial ice nor snow. And it happens to be able to retain a lot of water. So it can soak up a lot of water. And what happens is they don't necessarily know how thick the fern layer is. because it is underneath the snow on the surface, and it can retain a lot of water, and so the water might not even percolate down to the rocky area at the bottom of the ice sheets. If a lot of it's retained in the firn, then when winter comes, that water will freeze again. So firn is, it's a very, very important part of the dynamics of ice sheets, and it's something that is very, very poorly understood. Um, but anyway, a lot we don't know about ice sheets. And then in terms of the global climate models in general, there's a lot that we don't know about how the climate feeds back on the biosphere. I'm going to focus in on the last one because they think it was really, really important in the history of extreme warming events, and there have been a few very, very extreme warming events in the history of the Earth, what they call lithospheric feedback, specifically methyl hydrates. So in cold ocean water with a lot of pressure and a lot of methane gas, you can form these ices that are part methane, part water, but they become a solid. And these ices, and they're denser, so they don't float like water ice does, so they stay down there under the water. And these ices turn out to be relatively unstable. If they warm, they can quickly bubble away, and all the methane can come bubbling out of the ocean relatively quickly. And there is a lot of this methyl hydrate ice in the ocean. So as the ocean warms, this methyl hydrate ice could start to evaporate and the methane could go into the atmosphere. I think you know that methane is a very potent greenhouse gas, and that can start a runaway process where the melting of methyl hydrates warms the earth, which melts more methyl hydrates, which warms the earth, which melts more methyl hydrates. And like I said, they think that this particular feedback has been very, very, very important in dramatic warming events. There have been, like I said, some very dramatic warming events in the history there. And specifically, we may be in a really dangerous spot right now because the Pleistocene, the era of the ice ages, lasted so long that we've got a bigger store of frozen methyl hydrates in the earth right now than is typical. So it's not only that the last 10,000 years have been unusually stable, it's also that the period where we were alternating between, where there were periodic ice ages in the northern hemisphere and Antarctica completely covered with ice, that long-lasting cold spell in the Earth's history has been an opportunity for us to build up a lot of these methyl hydrates. And if that long-lasting cold spell comes to an end, which it seems that it is, then what we may see is really, really, really rapid melting, so that we might see not only the melting of Greenland, but the melting of Antarctica, and a completely different climate system, and a set of conditions under which it's very hard to imagine that human civilization with cities and all the complexities of human society would exist anymore. Okay, so what to do? First of all, Google IPCC 5, and hopefully it'll autofill IPCC 5th assessment report for you. There are 3 things that I'd like you to look at. Click on each of them. And when you click, what you'll see is the summary for policymakers. Download that and then just glance through it. Give it a look-see. See what they're talking about. And as you're looking, if you become fascinated and you want to understand every word and read it from cover to cover, great. I'm thrilled. But as you're looking, ask yourself what a young person would need to already know about the climate in order to make sense of this report, because these are really, really important documents in that they are written by the scientific community, that they do a good job of summarizing at least the consensus view of the scientists, and they are meant for educated lay people. So the intended audience is not other scientists, it's college graduates, people like congressional staffers and bureaucrats in the UN and interested lay people like me. So these are meant to be read not by scientists but by lay people, and it would be very helpful to your students if by the time they graduated college this was something that they could pick up on their own and make sense of. So why don't you pick it up, and why don't you see what you think you need to understand, or if you feel that you understand every word, what you think another person needs to understand to make sense of it. So I'm operationalizing climate literacy as specifically the ability to read the summary for policymakers from the IPCC and look at it and think about what somebody needs to know about the climate system. Climate modeling is a huge part of what's discussed in the IPCC. And there's also a lot of discussion of technology because, like I said, climate models are technology, but you'll also see some mention of scientific technology in there. And again, if you could discuss this on Edmodo, that would be great. And again, thank you very much for your attention. I am sorry that I was so long-winded, but I seem not to be able to help myself.